Welcome to the world of the AAV-9 VANTAGE program, a groundbreaking leap in aerospace engineering. This project is not just another aircraft, it's a full-spectrum demonstrator for asymmetric electrostatic propulsion. Unlike traditional platforms, VANTAGE integrates fine-scale geometric asymmetry, advanced field control, and real-time AI modulation. The mission is clear: to prove that asymmetric electrostatic pressure forces can be harnessed for scalable, maneuverable, and tactically relevant flight. This is the first credible step toward a new era of propulsion, where physics and engineering converge to challenge what's possible in aerospace. VANTAGE is not a fighter, not a transport, and not a reconnaissance craft in the traditional sense. Its primary mission is to demonstrate controlled lift, maneuvering, and sustained flight using asymmetric electrostatic propulsion. Secondary roles include validating air-driven field shaping, testing metamaterial-based permittivity control, and characterizing plasma boundary interactions, the long-term vision. To serve as the baseline for future high-altitude, low-signature, and orbital transfer vehicles, VANTAGE is the first operational step into a new propulsion paradigm, setting the stage for next-generation aerospace systems. The VANTAGE program stands on nearly a century of incomplete breakthroughs. Early electrostatic asymmetry research in the 1920s to 1960s, led by Townsend Brown, planted the conceptual seeds. Later, high-voltage dielectric research in the 1970s to 2000s proved the physics, but lacked the materials and control systems for scaling. Modern breakthroughs, metamaterials, solid-state inverters, and AI field modulation have finally created the technological environment necessary for the VANTAGE system. Each era contributed a vital piece, culminating in this ambitious project. Previous research faced major hurdles: coarse asymmetry, slow field control, and unpredictable plasma interactions. Materials couldn't sustain the required voltages, and no system could coordinate thousands of tiles in real time. The VANTAGE program resolves these with fine-scale asymmetry at the tile, dielectric, and electrode levels, plus AI-driven field control. Real-time sensor fusion and adaptive plasma envelope control make the architecture scalable and robust. This is the first complete, physically grounded, and scalable electrostatic propulsion system. The VANTAGE program is defined by 5 core objectives: demonstrate sustained lift, achieve maneuvering with polyphase modulation, validate AI field modulation, characterize plasma interactions, and establish scaling laws. These objectives are not speculative, they are engineering-driven, with each milestone designed to push the boundaries of what's possible in practical aerospace propulsion. Success will mean a new propulsion mechanism, a new design philosophy, and a credible path toward reactionless thrust. The VANTAGE airframe is a lenticular multi-shell structure. This shape isn't just for aerodynamics, it's optimized for electrostatic, dielectric, and plasma interactions. The saucer profile offers uniform field distribution, minimal drag, and maximum surface area for EPF tiles. Its curved shell distributes mechanical loads evenly, ensuring high stiffness and vibration damping. Every aspect of the geometry is engineered to support the unique demands of asymmetric electrostatic propulsion. VANTAGE's structure is built on a 3-shell system. The outer shell houses EPF tiles and manages plasma boundaries. The midshell provides mechanical strength with shape memory alloys and carbon-titanium composites, while the inner shell protects avionics and power systems. Each layer is engineered for its specific role, ensuring that the craft remains robust, efficient, and safe under extreme operational conditions. What sets VANTAGE apart is engineered asymmetry at every structural level. The hull's upper and lower shells differ in curvature and mass distribution, creating field line bias. EPF tiles feature non-uniform dielectric thickness and directional microgrooves, producing microscale thrust vectors. The hull manipulates plasma behavior with surface texturing and ion mobility gradients. Even AC-DC timing is asymmetric, generating traveling electrostatic waves for thrust without moving parts. Heart of VANTAGE is the Electrostatic Pressure Force (EPF) propulsion system. It generates thrust by exploiting asymmetric pressure gradients across a multi-tile, multi-phase field control shell. Each hexagonal EPF tile contains a layered dielectric stack, embedded electrodes, and integrated sensors. AI coordinates the tiles, modulating waveforms in real time to maximize thrust and maintain stability. This system is physically grounded, asymmetrically engineered, and scalable. VANTAGE divides its hull into 12 radial sectors, each with independent waveform drivers and local AI nodes. These sectors can operate in DC, AC, polyphase, or pulse modes, enabling static lift, dynamic thrust, and evasive maneuvers. The AI system synthesizes thrust vectors, optimizes waveforms, and protects the envelope from breakdown. Optical mesh communication ensures sub-millisecond coordination, making the system highly responsive and resilient. Powering the VANTAGE is a hybrid system. A compact solid-state microreactor provides continuous output, supercapacitor banks deliver peak surges, and auxiliary batteries ensure backup. Power is distributed via multi-ring high-voltage buses, with sector isolation and A-controlled routing. Local waveform drivers on each tile enable precise AC-DC modulation. The system is engineered for redundancy, survivability, and efficient energy delivery under all mission profiles. VANTAGE's flight control system is a distributed AI architecture, integrating a multi-domain sensor suite. Redundant AI nodes manage thrust vector synthesis, waveform modulation, and field envelope optimization. External sensors map electric and magnetic fields, plasma density, and terrain, while internal diagnostics monitor structural strain and system health. The AI ensures inertial safety, crew protection, and adaptive response to environmental changes, enabling precise and autonomous control. Crew Capsule is a shock-isolated survival module, centrally embedded and surrounded by high-voltage rings and AI nodes. Its elliptical pressure vessel, gimbaled mounting, and inertial dampers ensure survivability under high-G maneuvers. Life support includes active thermal regulation, CO2 scrubbers, and radiation shielding. Emergency protocols are fully autonomous, with AI managing descent, parachute deployment, and life support for up to 2 hours if needed. VANTAGE is a physics demonstrator, designed to test lift, maneuvering, field envelope control, and plasma interactions. It operates in hover, maneuver, and pulse modes, adapting to atmospheric or vacuum conditions. Performance ranges from 0-30 km altitude, with cruise speeds up to 500 ms and pulse surges over 1000 ms. The system is engineered for survivability, with protocols for fault recovery, emergency descent, and redundant power and life support. Electrostatic propulsion relies on dynamic interaction between electric field geometry, dielectric behavior, and plasma boundaries. The field envelope is actively shaped by AI, adapting to hover, maneuver, or pulse modes. Plasma boundary layers are controlled via surface microgrooves and permittivity gradients, ensuring efficient thrust and stability. The system is designed to recover from dielectric breakdown, plasma detachment, or phase desynchronization, maintaining operational integrity. VANTAGE is engineered for survivability under extreme conditions. Shape memory alloy ribs absorb shock, multi-shell isolation protects internal systems, and AI compensates for asymmetric damage. Power redundancy includes dual AI cores, sector isolation, and emergency battery backup. Emergency protocols cover envelope collapse, phase resynchronization, and autonomous descent, ensuring crew safety even in combat or system failure scenarios. VANTAGE system is the result of decades of research, from early electrostatic lift theories and asymmetric capacitor experiments to modern breakthroughs in AI-controlled waveform systems and plasma envelope shaping. Each generation contributed to the technical milestones that define VANTAGE today. This craft is not just a technological achievement, it's a bridge between theory and operational capability, setting the standard for future aerospace propulsion. VANTAGE's superiority lies in its rigorous mathematical foundation. Unlike speculative gravity theories, every aspect, from electrostatic pressure equations to AI waveform modulation and plasma modeling, is engineered, tested, and validated. The system's analytical backbone enables simulation, validation, and future scaling. This is what sets VANTAGE apart, a physically grounded, operationally credible approach to asymmetric electrostatic propulsion. In summary, the AAV9 VANTAGE program consolidates decades of research, engineering, and innovation into a single, operationally credible platform. Its architecture, mission, and technical rigor set the foundation for the next generation of aerospace propulsion. As we look forward, VANTAGE is not just a craft, it's a doctrine for future exploration, a testament to the power of engineered physics, and a beacon for what's possible when science and ambition unite.